next up is Brian, who will continue to tell us about XQCD.
Great. So as Dave said, the main thing I want to focus on for the next 2 lectures is super QCD, which is really why we built up all this technology. Before we get to that, so my main goal for the next 2 days is just to map out the vacuum structure of super QCD for different numbers of flavors and colors. Before we get to that, though, I have to tell you a little bit about how you find a supersymmetric vacuum to begin with, because this isn't something that we've talked about yet. So let me just really briefly review how to find supersymmetric vacuum. Okay, so this is stuff that most of you probably already know, but I just want to make sure we're all on the same page. All right, so remember that. So basically what I want to derive for you is I want to derive the scalar potential for n equals 1 supersymmetric theories. So recall that the supersymmetric algebra, or n equals 1 algebra, looks like this. Anticommutator q bar is momentum. And it's pretty easy to derive from this the Hamiltonian, which is just P0. So you can show that the Hamiltonian of this system, or I should say the Hamiltonian that you get from this algebra, is just something that looks like this. And I'll write it as it's the sum of 4 terms: Q1, Q1 dagger, Q1 dagger, Q1, whoops, Q2, Q2 dagger, Q2 dagger, Q2. Which you can see if I want to look at the expectation value in some vacuum state, whatever it is, of the Hamiltonian, this is just a sum of squares. So the expectation value is always going to be greater than or equal to 0. And in fact, the only time it's equal to 0, you can see, is that if my vacuum on both sides, this thing I've written as omega here, so H equals 0 if I have a supersymmetric vacuum. So this is how I can find, if I can derive my scalar potential, this is how I can find supersymmetric vacua, is by looking for the 0 energy states, by looking for the minimum of the potential. And if I can never have, if I write down some potential that has no 0 minima, then supersymmetry is going to be broken. So my criterion for unbroken SUSY for the vacuum is that I can find some potential which is 0 at some minimum. And my potential will always have to be greater than or equal to 0. So this is really the minimum. And this is something that Seiberg is going to talk about at great length next week. All right, so I'm not going to talk a lot about supersymmetry breaking. I'm just going to be concerned about finding supersymmetric vacua. But Nadi will tell you a lot about recent results in supersymmetry breaking. OK, so what I want to do now is I want to use the technology that we've established for writing down supersymmetric actions to figure out what the scalar potential is. All right, well, this isn't so bad. So let's see. There are going to be two different contributions to it. So let's see, how do I want to do this? If I have, let's consider what happens with the part of the Lagrangian with the auxiliary field F. So if you remember in the kinetic term, I have something that looks like F star. It's just an auxiliary field. It's perfectly quadratic and has no dynamics. And then if I expand out, for my superpotential, I have terms that look like d2 theta w of phi, if I expand this out, if I expand out phi, well, phi, its square term, its theta squared term is f. So I'll pick out a term that has a theta squared term here that has an f and one derivative of w. So I'll get something that looks like dw d phi plus, maybe I'll use bars instead of stars, f bar dw bar d phi bar. And I'm going to be kind of loose about whether I use the superfield here or its scalar component, because it won't really matter. All right, so I can figure out the equations of motion for f and f bar here. Right, if I just integrate out f, if I just take the derivative with respect to f, what I'll get is that you can see f bar equals minus d omega d phi, and similarly f equals minus d omega bar d phi bar. And so from this I can just plug everything in, and I get the contribution to the scalar potential from here is just going to be, well, let's see, I'll get absolute dw d phi squared, but then I get two of those with minus signs. The scalar potential comes with a minus sign anyway. So I guess I get that the scalar potential is just dw d phi squared. And of course, if I have more than one of these fields, it's easy enough to just rewrite this as a sum of squares. So these, if I want to solve these, if I want to solve the equations for a supersymmetric vacuum here, I need to set this equal to 0, which means that I need to solve, because this is a sum of squares, I just need to solve dw d phi equals 0. And these are the f terms. OK, so that's one set of equations I need to solve for to find the minimum of my potential. And notice it's an easy thing to do. I just take a derivative and solve it. OK, so that's one contribution to the scalar potential. There's another, though, coming from the d terms. So remember my Lagrangian for my supersymmetric gauge theory was I had d4 theta and then a Kähler potential, which I'll be interested in non-abelian theories, so I'll just write this e to the v. And then I had my usual kinetic terms for the vector multiplets, which I'll just write as trace w squared plus Hermitian conjugate. And so let's see. When I didn't really write this thing out in components. This one I did write out in components. And the d term from here, this just becomes 1 over 2g squared. I'll write dA. This is just a group index. This thing I didn't expand out in components, but it's not too bad to see what happens. Where can I write this? I'll write this over here. Remember that my vector superfield, maybe I'll write it down here, has a bunch of stuff plus a term like, and let me put a group index on this, theta to the fourth dA. And so you can see a theta to the fourth term here is just going to come from the lowest component of these superfields on both sides times this d term when I take this exponential. So the term I get over here, now this v, remember v is BA times a group generator. So this term gives me something that looks like 1/2, let me write it like this, phi I star dotted into the group generator. And then there's a dA out front as well. And here all this means is that I've multiplied these, I've contracted these through. This has some group indices, and these transform in some representations. And I haven't been specific about what representation they transform in yet. This is just some nice singlet thing. OK, so this is the d terms in the Lagrangian. Of course, there's other stuff. Now, if I find the equation of motion for the d terms here, right, all I do is I take a derivative with respect to d. It's very easy. I get that. And then plus 1 over g squared dA. There's 2 of them, so it cancels off this 2, equals 0. And now I can solve for d. dA is just minus g squared over 2 times this thing. Great. And now if I plug this all in, I can do exactly the same thing as I did over here. Which is not so bad. And so if you plug this all in, what you get is that the scalar potential goes like g squared, I think, over 8, sum over a. So implicitly in this thing, I probably should have written it explicitly in the Lagrangian here. I've written a sum over this I index, which labels what the scalar fields are. So let me just restore that. These things squared and then summed over a. And once again, I want this to be equal to 0. So the so-called d terms here just involve solving this equation. Which often isn't too bad. And we'll do an explicit example of this in a little bit. Okay, so my total scalar potential is this plus this. You can see in order for it to be 0, I need that any one of these terms that I'm squaring has to be equal to 0. All right. Notice one thing, by the way, that I'm not including here is an Fi term, mostly because what I'm going to be interested in is non-abelian anyway, but you could put them in and they would contribute to the scalar potential as well. But I'm not going to say anything about Fi terms. All right, great. So the point is that when you solve these equations in supersymmetric gauge theories, you often get some very interesting structures. And in particular, you can get entire manifolds of vevs you can give to these scalars. So let me just do one very, very simple example to show you this. So let me do something that's not a gauge theory, so I don't even have to do the d terms. Although eventually, I mean, in another like 5 seconds, all I'm going to be concerned with is solving the d terms. I'm going to be looking at super QCD without any super potential. So let me do an example, which is pretty standard. This is the so-called XYZ model. This is just a theory of 3 chiral superfields. No gauge anything, no gauge interactions. And all this is just some superpotential, which looks like, I don't know, I'll call it H times X times Y times Z, where each of these is a chiral superfield. All right, so what are the F terms here? There are no d terms because there's no gauge interaction, there's no vector supermultiplets. So the F terms here, well, it's easy enough to write down. dw dx is yz, et cetera. It's just the product of any 2 of these. So what I need to solve is xy equals yz equals xz equals 0. And the solution to this is apparent. If I take any two of these superfields and set them equal to 0, I can solve these equations, and then the other one is unrestricted. It can be any complex number you want. And I again should say that I keep saying superfields, but really what I'm talking about is the scalar component of these superfields. That's the only thing I can give a vev to without breaking supersymmetry. So, so the solutions of these, so to solve these, you can write, all right, well, x equals y equals 0. And again, this is code for the expectation value of the scalar component of x equals the expectation value of the scalar component of y equals 0. And z is anything etc. X equals z equals 0. Y equals anything. I guess union. What haven't I done? Y equals z equals 0. X equals anything. And by anything, I really mean any complex number here. Right? So if you were going to kind of draw a little cartoon of this, you can see that there are effectively three branches of these vacua parametrized by different complex numbers. And these intersect at some point when these guys are all equal to 0. All right, so if you like, this is the z not equal to 0, x not equal to 0, y not equal to 0 branches. So this kind of structure of different vacua, of different flat directions for the potential, is what we call a moduli space. So I've just solved for the classical moduli space of this theory. All right, so what I actually generally want to do, though, is this is a very boring example. I mean, there's no gauge interactions. I mean, it's kind of a cute picture, but that's about it. Oh, I erased the d terms. Oh well. So what's more interesting, and really what I'm going to be concerned with for the rest of what I talk about today, is I want to find the moduli space of gauge theories, and in particular gauge theories with no superpotential. So the moduli spaces I'm going to be concerned with, in general, you have a moduli space in which you solve the f terms and the d terms, then you just mod out by gauge transformations. But from now on, we're just going to set in everything we do here, and of course you don't need to do this. Lots of interesting examples don't. We're going to set our tree level superpotential equal to 0, which actually does still yield a tremendous amount of very interesting structure. So in this case, the moduli space, the classical moduli space, which let me write as script m classical, is, I mean, it's very simple to write down, right? You just solve d equals 0. It's the set of all solutions to solving the d terms. But of course, in a gauge theory, you want to mod out by, you don't want to overcount things, so you want to mod out by gauge transformations. All right, this is great, and we'll actually do this. But there's actually a better way of parameterizing the moduli space. I'm just going to state this without proving it, but hopefully you'll believe that it's plausible. And in fact, I'll show you in a specific example a little bit later on that you really do get the same thing, which is that I can also think of the moduli space as good coordinates, right? I don't want coordinates that are going to transform under gauge transformations. Good coordinates on the moduli space are going to be gauge invariants. So another way of thinking about the moduli space is I form a set of gauge invariant coordinates, so let's say gauge invariant monomials, out of whatever fields I have in the theory, subject to whatever relations I might have between them, right? If I form a bunch of gauge invariants in some arbitrary gauge theory, I'll have some relations between them. And classically, all I want are the classical relations. These relations might get modified, and in fact will get modified quantum mechanically, and we'll see an example of that later on. But if I just want the classical moduli space, I just mod out by, I'll say, classical algebraic relations. And I'll do an example of this towards the end of the talk today. Now, I haven't proven this for you, and I'm not going to. But hopefully, you'll see in an example that this actually works. All right. So this is the kind of moduli space we're gonna study today, and in particular, I want to study this in sort of the flagship example of supersymmetric gauge theories, which is super QCD. So before we study super QCD, I want to do this over here. I need to define super QCD. All right. So I should say before anything that more or less everything I'm doing today and tomorrow is due to Nadi Seiberg and collaborators. So this type of language, and in fact many of the analyses I do is really due to Seiberg. And he's going to use a lot of this language very extensively when he talks about supersymmetry breaking in super QCD. So in a very real sense, the purpose of my talks here is to set up the vastly more interesting talks by Seiberg next week on supersymmetry breaking. So pretty much everything I say, aside from the last lecture, is stuff that was known 10 years ago. So the stuff I'll talk about on Friday is a little more recent. OK, so what's super QCD? Oh, what's QCD? There are many speakers here who have already talked about this in a lot more detail than I will. But from my perspective, what's QCD? QCD, well, it's a SU3 gauge theory with some left-handed quarks transforming in the fundamental, and some right-handed quarks in the anti-fundamental. I don't care about whether they're SU2 doublets or not. And if you want to include all 6 flavors, there you go. So super QCD, all we're going to do is generalize this by promoting each of these quarks to superfields. And in fact, I'm going to make it even more general. I'll let the number of colors and the number of flavors just be arbitrary. And we'll see that we get very different physics depending on what those 2 parameters are. So super QCD, all I want to do is let's take a gauge group SUNC, and C for the number of colors. And I'm going to have some chiral superfields transforming in the fundamental of SUNC. And I'll take some other chiral superfields. So I'll call these guys Q and these guys Q twiddle. These are both chiral superfields. Only one transforms in the fundamental representation and the other transforms in the anti-fundamental representation. And I can put in as many flavors as I want, but I want, for the time being, an equal number of flavors of each. So we'll take I equals 1 up to some number nf. OK, so from this, just from this, without any tree-level superpotential, and at the moment I'm not going to add masses for any of these quarks or anything, although you certainly can, that'll change the analysis that I do slightly. And in fact, I'll show you some examples of that later. I can write down my SUSY Lagrangian for this thing. It's pretty easy. And I do that in order to find the moduli space. So let me just, do I want to do that? You know what, maybe what I should do first is I should write down the global symmetries of this theory, since this is going to be something that's very important for figuring out the physics. All right, so what are the global symmetries of this theory? Let me just say the symmetries. So I've got my Q's, I've got NF Q's, I've got NF Q tildes. As I said, I have an SUNC gauge group where Q is a fundamental, Q tilde is an anti-fundamental. Now the global symmetries are pretty straightforward. I can just do a UNF rotation on either of these quarks. So let me write this UNF times UNF as SUNF times SUNF. This is just the standard thing, times U1 baryon times U1 axial. You can see that I'm not doing anything strange at all here. But I also here have an R symmetry. And this is something that I will talk about in a lot of detail as we go on. So let's say I'll take these guys to transform in the fundamental of one but not the other, singlet of the other. These anti-fundamental. And I can assign baryon charges the usual way, 1 and -1. I have an anomalous axial symmetry, which I'll write anyway. And then the U1R, let's wait on this to assign those charges. And this is something that we'll need to do. And I think we will actually, yeah, we'll do this later today. So here's a list of the gauge and global symmetries. That is completely illegible. Of SQCD. All right. So I'm going to be drawing these kinds of charts routinely throughout the next couple of days. OK, great. So there's that. What I want to do now is I want to find the moduli space of this theory. I want to find what vevs I'm allowed to give the squarks. So there are a couple different ways of doing this. Now, as you can see up here, I can kind of do two different things. I can jump straight to the gauge invariant monomials, or I could actually solve the d terms. And because it's instructive, for this first case, I'm actually going to solve the d terms for you. And you'll see, I'll show you that I really get the same physics either way. So let me start by considering the following range of flavors and colors. Let's start with, so the question I want to ask is, what's the moduli space for NF less than NC? All right, so today what I'm going to do is I'm going to start with NF less than NC, find the classical moduli space. Then we'll go to NF greater than equal to NC, find the classical moduli space of that. Then I'm going to come back to this and find the quantum moduli space. And finally, I'll end up today with the quantum moduli space of NF equals NC. And then the subject of what I do tomorrow will be entirely the case where NF is greater than NC. And I guess one thing I should say right away here is you might say, well, I know, there's some restriction on how much matter I can put in this theory to still make it asymptotically free. So you can compute this. This is a slight aside. Everything I do, obviously, I want this theory to be asymptotically free. So the one-loop beta function, remember, from what I wrote down yesterday, was 3/2 Casimir of the adjoint minus 1/2 sum of the Casimirs of a bunch of the representations. And in fact, I did this example yesterday. This is 3NC minus NF, and I want this to be 0. Remember, because I wrote this with a minus sign in the one-loop beta function. So as long as, so for asymptotically free, as long as NF is less than 3NC, we're great. For NF greater than 3NC, the theory is IR free, and there's not a hell of a lot to say. Right, so everything I do is going to be in this range. So certainly NF less than NC is here. All right, great. Let's solve the D terms. You know what? Let me keep that. No, I'll erase that. Great. All right, D terms. So let me, as I promised before, write out the Lagrangian. So in my kinetic term, what do I got? I got some Q's transforming in the fundamental representation. I'm just going to kind of use a shorthand notation, but hopefully it'll be clear what I mean. So this is in the fundamental. So really here, this is some vector superfield times a generator in the fundamental. Plus I have my Q tildes, Q tilde bar. I could put a dagger there too, but it doesn't matter. And I will just schematically notate this e to the minus v, where minus v is meant to indicate not minus v, but just the anti-fundamental. All right, so there's my Lagrangian. My D terms I wrote down before, right? The D terms, what are these? These are just, very generally, this over all the fields in the theory. So what is this for super QCD? Well, let's see. For super QCD, let me make sure I get my indices the way I like them. This guy has a, oh, you know what? Let me change these, since I will actually care about this sort of thing. I'll just use an index up. This I is a flavor index, so this is transforming in the fundamental of the SUNF. This one over here. This guy transforms in the anti-fundamental of SUNF. So let me just keep that straight. So translating this over here, what do we have? Well, let's see. I have Q bar I. So that's a flavor index. This also transforms in the anti-fundamental, because it's Q bar, of the gauge group. So that's going to be a flavor. That'll be a color index. Let's see, and then I have a generator. In the fundamental times QI B. And then the same thing for the Q tildes, only I'll change my placement of the indices and make this a generator in the anti-fundamental. So let's see, what do I have? I know this tilde bar notation is kind of hideous, but sorry. So let's see, Q tilde transforms in the anti-fundamental, so this is going to look like this. So I'll start to compress some of this notation in just a second. All right, so these are the D terms. I want to set them equal to 0. All right. So I can solve these now. These are actually very easy to solve in a way that unfortunately doesn't kind of generalize to arbitrary theories. So what can I do? Well, it'd be nice to get rid of this generator. But you can, because you know there's a relationship between the generator of a fundamental and the generator of the anti-fundamental. I know that the generator of the anti-fundamental is minus the transpose of the generator in the fundamental. So what can I do? Well, I can just put a minus sign there, take a transpose, and rewrite this thing. So I can rewrite my d terms. Let me factor out a generator in the fundamental. These guys won't change, the q's. And I'm going to drop the parentheses because hopefully now it's clear that I and j, or just I here, are flavor indices, and A and B are color indices. QIB, QIA. And then let's say I need to relabel indices and I get a minus sign, but it's clear what you get. Q tilde bar IB Q tilde IA. All right, so these are the d terms. Now this is some nice Hermitian matrix. So I can write this. So let me rewrite this as this generator in the fundamental times some matrix I'm just going to call NBA. And now I can expand NBA in. I know that the generators of the fundamental of SUN along with the identity will form a basis for these guys. So I can write NBA in full generality just as a delta function plus some coefficients times these guys. OK, cool. But what is this? This is just the trace of these two matrices. So I know that when I multiply by, if I actually want to solve this thing equals 0, well, this thing is automatically 0. It doesn't place any restriction on C0. But these, when I take the trace, they will be non-zero. Right? There's some Casimir. So in solving this equation, it's necessary that all these coefficients CA here are identically 0. Great. So already we're making progress. Cool. All right, so to solve the d terms, I see that all these non-C0 coefficients got to be 0, but C0 doesn't. So then all I need to solve is this guy. Equals some constant, this matrix, times the delta function. OK, great. So now this is where it gets a tiny bit, I won't say tricky, but you have to finagle it a little bit. But it's not too bad, because I have a bunch of flavor and color rotations I can do to kind of put this in a nice form.
So why is there a bar on only one of on the Q tildes but not on the Qs?
I'm sorry, say that again?
Why is there a bar on the Q tildes?
Oh, thank you. There should be a bar. Right there. Thank you, Joe. That's a. Did I routinely screw that? No, it was right there. I made a mistake. Okay. Thank you. Great. OK, so to solve this, it's not too bad. And let's see, how do I want to present this? I guess what I'll say is that I can write, by some suitable number of color and flavor rotations, I can write this guy. Is that what I wanted to do? Yeah. So what is this? This is some matrix that has NF of these indices, the I's, and NC of the B's. So let me just write this as a NF by NC matrix, where you can convince yourself that I can make this diagonal and set all these guys down here to 0 by some suitable number of color and flavor rotations. And then, OK, once I've done that, QIB, Q bar IA, you see this is going to be an NC by NC matrix. This is just going to give me along the diagonal the absolute squares of all these things. Q1 squared down through QNF squared, and then a bunch of zeros corresponding to these zeros down here. So this is an NC by NC matrix. OK, cool. So let's see. Now I know that this guy minus the Q tilde, the analogous version of the Q tilde, has got to be a delta function. So this has to be diagonal to solve the D terms in this gauge. Right? And let's see. Furthermore, what else can I say about Q tilde, or sorry, Q tilde bar Q tilde? I should add that in just a minute, I'm going to make this entire kind of irritating analysis moot by doing this in a much simpler way. So you can ask, why did I do this? And I'm not really sure. I mean, this kind of thing, because I should say, because I want to kind of do the D terms separately from the faster way and convince you that you get the same physics. So let's see. OK, so Q, this must be diagonal as well. But you know there are only, each one of these Q tildes is at most a rank NF matrix, right? NF is less than NC. So this thing must be at most a rank NF matrix. So it's got to have at least must have at least NC minus NF 0 eigenvalues. So in fact, in generality, I can write this matrix as a bunch of absolute squares, some of which may be 0. And then the remaining NC minus NF 0 eigenvalues are down there. I can do some flavor rotation to put it in that form. And what this tells you is then if you subtract this minus this equals some delta function, well, these components will always be 0. So the only way to solve the D terms is now by setting this coefficient right here equal to 0, right? Because I have these zeros down here.
Another question?
Yeah.
So you already used some color rotations to diagonalize.
That's right. So all I need here are actually flavor rotations. And I have another SUNF worth of flavor rotations to do this. All right, so partly what I did, I used the color rotations to diagonalize this. And then I solved the D terms. Right, so I said in the gauge where I picked this, to solve the D terms, this has to be diagonal. Okay? And then to write these eigenvalues in this way, I use the remaining flavor rotations. OK, great. So I got to solve. Yeah, so I should say that in the literature, people will lie to you sometimes and tell you could diagonalize this without solving the D terms. But that's clearly not true for precisely the reason you said. OK, so C0 equals 0. And what does this tell me? This tells me that these eigenvalues, well, these two matrices are exactly the same. These things have to be the same. The absolute square of each component here has to be the same. So generically, at some arbitrary point on moduli space, I'm going to give each of these quarks a Vev. OK, great. So now what I want to do, I want to do this simpler way of solving these equations. Wow. OK, the simpler way is to just write down some gauge invariants. Write down a basis for gauge invariant monomials. So what are my gauge invariants here? Well, NF is less than NC. I can't form baryons. I don't have enough flavors. So really, the only gauge invariants I can form here, so my basis, so here's the other way of finding the moduli space, is write down, I have gauge invariant monomials Mij, which are just, let's see, let me make my indices consistent.
Excuse me, I've got a question.
Yes.
So you've used one basis to diagonalize the first matrix and another basis to diagonalize the second.
No. So what I've done is I've used one basis to diagonalize the first. And then I said in that basis, to solve the d terms, the other one needs to be diagonal as well. Okay? So that's a big difference. So, okay, so my gauge invariants here, a nice set of gauge invariants are these mesons where I've contracted color indices between these two. I haven't written them there. Well, how many are there? There are NF of these quarks and NF of these quarks. So they're NF squared. NF squared. People use the term mesons for these guys. And in fact, you don't expect any algebraic relations between these. So that should be the dimension of your moduli space. You should have NF squared flat directions. Where I can give these mesons any value I want. Now you might say this looks nothing like what I did over here, really. But it actually is exactly the same physics. Because what's happening over here? What's happening over here is I showed you that in order to solve the d terms, we have to give these quarks I should say a solution to the d terms generically is to give these quarks non-zero vevs. Now you can have some of these vevs, or in fact all of these vevs be zero as well, but let's take the generic case where they're all non-zero, just like that would be saying over here, all these guys are non-zero. Well, if I give these fundamentals vevs, I expect to Higgs the theory. So what I expect the physics over here to be, once I put in these vevs, is the physics of the Higgs mechanism. So there's a super version of the Higgs mechanism in which a massless vector multiplet eats a massless chiral multiplet to form a massive vector multiplet. I'm not going to go through the details of that. It's totally worth doing though. But over here, so what did I do? I gave this is Higgs. So I expect my theory over here. Let's see. I started with an SUNC theory, and I gave a vev to NF fundamentals and anti-fundamentals. So I expect this to Higgs the theory to SU NC minus N. And in fact, let's check some counting. So how many gauge bosons got a mass? So number of massive gauge bosons, well, let's say I just take the rank of that guy minus the rank of this guy, which you can see is 2 NCNF minus NF squared. But if I just give vevs to everything, if I just give vevs to all my flavors here, it looks like I gave 2 NC, so I gave 2 NC NF vevs, right? I have 2 NF flavors and they're each in an NC dimensional representation. But you can see the discrepancy between these two. I only needed to eat this number minus NF squared, right? So what I have left over, the things that didn't pair up, I have NF squared left over. And these are exactly the NF squared scalars that I expect to parameterize the moduli space from this argument over here. Right, so the physics, you see that the physics is pretty much the same, but in solving the d terms explicitly, you can see these vevs, and then you just get the usual Higgs mechanism. Writing this down gives you exactly the same dimensions in like 1/10 of the amount of work, but I think this is a useful comparison between the two. Notice that I haven't done the case where NF is greater than or equal to NC, or even NC plus 1, where we'd expect to break this group entirely. And I'll do that in just a few minutes. OK, great. So let me move on. Yeah, Dave.
What's happening with the counting is that you have these vevs for the Q's and the Q tildes, which are equal, but you can still now act with the flavor symmetries to get the NF.
Yeah, that's right.
So
That's right. So there's still
like
flat
the
directions
Lagrangian
here.
of QCD, essentially.
Yeah, that's exactly.
That extra part.
OK, great. So let me move on to the next case, which I think I may do in slightly less detail. So let me move on to NF greater than or equal to NC. So I should say, what do we expect to happen here then in NF less than NC? We expect to get some scalars, which are singlets under this gauge group, and they have some. I didn't compute the Kähler potential, but you'll get some nonlinear sigma model for these singlet scalars times this SU NC minus NF Yang Mills. There, super Yang. All right, so let's move on to NF greater than NC. I'm not going to solve the D terms explicitly like I did this time. It would take too long, and it's not that much harder than what I did. What you find is that now, of course, you're not going to have zeros along the that constant C0 doesn't need to be 0 anymore. So you get that these things will still generically have vevs, only there's some kind of universal constant, which is basically C0, which relates the two. The point is that if you do solve the D terms generically, you give all these things vevs, just like you did over here. So all right, NF greater than NC. Let's just write down gauge invariance. So let me jump to this last step. Well, we have these mesons that we wrote down. Again, where I've contracted color indices here. But now I have enough flavors that I can form fully anti-symmetrized. I can fully anti-symmetrize on the color index, right? With NF less than NC, those things would automatically vanish because I'd have to repeat a flavor index. But here I don't have to. So I can form the analog of baryons, which let me write like this, where I specify some number of flavors. So again, A is color, I is flavor. I and C, A and C. And I anti-symmetrize these by all the color indices. And I can similarly do the same for the anti, if you like, baryons with the Q twiddles. So all I'm doing is I'm just anti-symmetrizing along all the color indices. In NF less than NC, these would vanish. OK, great. So how many of these do I have? So let's count them. I have NF squared plus, for each one of these, I have NF choose NC possibilities. Great. All right, well, what's the physics we expect here? Again, we expect the physics of the Higgs mechanism, except here where we completely break the gauge group. So let's do the same counting we did over here. I have, let's see, how many vevs did I give? I gave, if I just give vevs to all these quarks, again, I have 2 NF and C. But then I expect to lose a bunch of these to the gauge bosons to give them a mass. But there's a mismatch here. Which is that this number, you can plug in different values of NF and NC, is less than this number up here. So I've overcounted my degrees of freedom. And you might say, OK, what happens? The answer is fairly straightforward. The answer is that, of course, when I formulated my description of the moduli space originally, I didn't say it was just the gauge invariance. I said it was the gauge invariance subject to some possible classical relations. And the answer here is that you do have classical relations between these guys. So let me do a simple case, which is just NF equals NC. So let's just do a quick example. Oh, sorry, actually, let me write down the general version first, and then I'll specialize. One thing you can use is that you can use that if I take a bunch of anti-symmetric tensors like this, I can write these as some product of delta functions where I anti-symmetrize. So for example, if I have E A1 through NC and E B1 through BNC, I can write this as A1, B1, A2, B2, ANC, BNC, where I anti-symmetrize in one of those indices. And from this, I can see that if I multiply two baryons together, right, I can recontract their color indices and form something in terms of the mesons. So one condition from this is that B I1 through INC times B twiddle J1 through JNC, and I won't work out this explicitly, although it's easy enough to check. This is just a bunch of the mesons appropriately anti-symmetrized. So there's one constraint. Another constraint, which I won't write down in detail because I actually won't use it that much, is just that if I take one of these baryons and I multiply it by a meson, and then I anti-symmetrize in more than NC color indices, I expect that thing to be 0. So anything with more than NC color indices anti-symmetrized equals 0. And that does become important, but I won't use it in the example I'm about to write down. So this, for example, restricts things like baryons times mesons. All right, so let me do an example. This example where NF equals NC, which is what I was about to do. So let me just look at the counting here. For NF equals NC, this number is clearly NF squared plus 2. And this number over here gives me NF squared plus 1, right? If I just plug in NF equals NC, I get 2NF squared minus NF squared plus 1. Right, so I have NF squared plus 2 gauge invariance and NF squared plus 1 leftovers. Well, what this tells me is there better be one constraint. And it's not too bad to see what it is here. It's in fact exactly this constraint. And I can rephrase this. Now if NF equals NC, an easy way of rephrasing this is by multiplying each of these, by contracting these with an epsilon tensor. So I anti-symmetrize all of these. I anti-symmetrize all of these. I anti-symmetrize all of these and all of these. And an easy way of writing this, where I've anti-symmetrized on the top and the bottom, is as a determinant of this meson matrix. So my constraint in NF equals NC so my constraint for NF equals NC is, let me write it in kind of the standard way you see. Star B just means I multiply that by an epsilon tensor. In fact, here there are no indices because I've contracted all those flavor indices. Star B times star B tilde equals the determinant of my meson. Okay. Great. So that's the deal for NF equals NC. For NF greater than NC, there's not kind of a simple set of constraints you can write down that are not overcomplete. But I'm not going to get into that at all. This particularly simple example is one where you can just write down a nice holomorphic constraint and then be done with it. All right, great. So the main thing I want to do now, are there any questions about this before I continue? So the main thing I want to do now then is derive the quantum moduli space for the case NF less than NC. This will probably be, depending on how long it takes, the last thing I do today. Right, so I've done two classical moduli spaces here. One thing I want to ask now is, what is the quantum moduli space for NF less than NC? And this is something that Nadi will use a lot in his talks. OK, great. So what do? I go back to this exactly the same game I played in the first lecture. Whereas I'm going to write down something. I'm going to try to write down, so what could possibly happen here? Well, one thing that I could possibly happen, I have a strong coupling scale in the picture. I could possibly generate some, dynamically generate some superpotential. So I want to ask if there's any superpotential I could possibly write down that is consistent with holomorphy and symmetries. Now, that won't guarantee you that it exists, but I'll talk about that in a minute. OK, so let's see, what do I want to do? Right, good. So what are my fields in this picture? I've got Q's and Q twiddles. I've got M's, which are the product of those two guys. Now, just like I did in the first lecture, I have another object in here that I can think of as promoted to a chiral superfield and promote this kind of explicit breaking, for example, of the R symmetry or the axial symmetry, or whichever one, in this case, the axial symmetry. I can promote that explicit breaking to a spontaneous breaking by thinking of the holomorphic strong coupling scale as a chiral superfield. So remember that I had this object, lambda to the b. This was the strong coupling scale, and the phase of this thing is the theta angle. Now remember, anytime I have an anomalous current, I can think of that anomaly as a shift in the theta angle. So what I'm going to do is I'm going to promote that to a chiral superfield and charge it under some of these symmetries. And that'll give us some selection rules for what can appear in the superpotential. And then, if you like, I have some gauginos as well, little lambda. All right, so my charges here, let me not write down the non-abelian global symmetries. Let me just write down U1b, UNA, UNR. All right, baryon axial R. And this is this R charge I promised we'd get back to. All right, so these guys are easy. We've done those a few times. This meson now has charge 0 and 2. R charge, let me just call, there's no reason to pick anything over anything else right now. Let me just call it little r. So the way I charge lambda to the b is by giving it the charge violation in whatever current that's anomalous. Said another way, that's what I'm doing to the theta angle. So this is not anomalous. That's 0. The anomaly here is just 2 times NF. It's the number of flavors. And the anomaly in the R symmetry, remember that if I have an anomalous U1 current, I multiply the charge times the Casimirs, and I add them up over all the fermions in the theory. Well, what do I have here? Let's see. I have a gaugino that's R charge 1. So the anomaly in the R symmetry, let's see, I have 2nc. Gauginos are in the adjoint representation. They have R charge 1. So this is 1 times 2nc plus 2nf of the flavors. Right? I have nf of these and nf of these. And these are in the fundamental. Right? So their Casimir is 1 in my normalization. But then this R charge that comes into the anomaly is R minus 1. Why R minus 1? Because in my conventions, this R is the charge of the superfield, which is the charge of the scalar component. And the charge of the fermion component, that's the next thing 1 theta up. Since theta has R charge 1 in my conventions, the fermion that's running through the triangle here to compute this anomaly has charge R minus 1. So I'm going to give this R charge that. Again, I just give it whatever the charge of the anomaly is. But you can see I have a free parameter here. I have R, right, little r. So why not pick little r to be anomaly free? Or why not pick little r so that the U1 R current is anomaly free? Well, you totally can. So let's pick little r equals, let's see, if I make it 1 minus nc over nf, then the U1R is anomaly free. Cool. All right, so now what do I want to do? I want to write down, so basically all these, this charge over here, I'm going to set to 0. So let me write down what are the possible effective superpotentials. Now, not only do I need them to be neutral under this, I need them to be neutral under the, of course, under gauge symmetry and under the flavor symmetries, the non-abelian flavor symmetries as well. So let me write W possible. Just something that I'm not saying this is generated yet, although it is. But this is the only thing that's possible. OK, so what do I want? I want something that's neutral under, well, baryon's pretty easy. Both of these are neutral under baryon. Something that's neutral under SUNF times SUNF flavor symmetry is the determinant of this. So you can see if I look at determinant of M, determinant of M has NF M's. So I'll have that times 2NF. If I look at the ratio of these two things, that's automatically, so the ratio of this and the determinant of M, that's automatically neutral under the axial current. So this could be, let's see, some function of, let me write it like this, lambda to the b over determinant M. Again, determinant to make this neutral under SUNF times SUNF. It just anti-symmetrize in all the SUNF industries, possibly times some number. There's not really much I can do with the R symmetry out here. Right now, this thing is still, this is charged under the R symmetry, right? So I'm not done. The R charge of this thing, what is it? This has R charge 0 by construction. The R charge of determinant M, let's see, it's minus, because M's on the bottom, NF, because I've taken the determinant, times the R charge of M over there, which is 2, times 1 minus NC over NF. Well, what is this? I can multiply this NF through and then move it around. This is 2 NC minus NF. So you can see there's only one thing I can do here to make this have R charge 2, which is to take it to the 1 over NC minus NF power. So this is not some general function. That's not consistent with being a superpotential. So W possible, the only possible thing is some number times lambda to the b over determinant M, 1 over NC minus NF. And in fact, so I'm not going to say anything about this coefficient here. My claim, or not my claim, I wish it were my claim, is that this is the dynamically generated superpotential in these theories. So let me say a little bit about this. And you know what? Let me write this explicitly. B is just 3NC minus NF. This is the one-loop beta function for these theories. And if you like, you can give this a subscript indicating that it's a strong coupling scale for this theory with NC colors and NF flavors. So let's talk about a couple cases. All right. The only time this is actually going to look like lambda to the B, in other words, the only time where you might hope that this is generated by instantons is when NF is NC minus 1. And in fact, explicit calculations have been done there. Finel and Pulio did SU2 with one flavor, and they checked that, in fact, this is generated by instantons. Okay? So you can check that this does come up from instantons. And then what you can do is you can add masses, for example, to the theory. And then you can generalize that. You can argue that that's related to NF equals NC minus 1 for arbitrary NF and NC. And then you can add masses and integrate out flavors. And what you get is exactly this form for the superpotential. So the instanton calculation plus integrating out massive degrees of freedom gives you some evidence that this thing actually does exist. And I should say, by the way, this is the superpotential that was first computed by Affleck, Dine, and Seiberg way, way, way before holomorphy or any of these techniques.
Capital D is important.
Yeah, capital D is very important here. Yeah. That is borderline illegible, but whatever. OK, so what's the physics of this? All right, let me just kind of do a quick thing here. I'm out of time, right? Yeah. OK, let me just say one last thing, and then I'll finish. So what's W? Well, W, just let me look at the scaling with M here. This goes like M to the minus NF over NC minus NF, all right? So what's the scalar potential look like here? Well, the scalar potential goes like dW squared, which you can convince yourself here is M to the minus 2 NC over NC minus NF. I think that's right. Yeah. So what does this look like? Here's V. Here's M. It looks like that. And in particular, there is no place where this hits a 0. So what you see is that there's no supersymmetric vacuum here for any finite VEV for M. So the quantum moduli space, well, that's a phi, is nothing. The quantum effects completely lift. So this is amazing, right? We had an NF squared dimensional moduli space in the classical theory. And what we find is that this dynamically generated superpotential completely lifts all those classical flat directions. So the quantum effects completely destroy the classical moduli space. One thing I didn't have a chance to talk about is what happens to the quantum moduli space for NF equals NC. It turns out that there you do not generate this superpotential. I mean, you can see right away that there's a problem with NF equals NC. But what you find there is that the constraint, which I don't have on the board anymore, this one up here, number 1, is actually modified quantum mechanically. And so what you see is there you have, you don't have a dynamically generated superpotential for NF equals NC, but you do have classical constraints that are modified quantum mechanically. And unfortunately, I won't have a chance to talk about those unless somebody asks me about them right now. So that's up to you. All right, so I'm done for today. Thanks. Okay, great.
I don't know what it is.
Sure.
Any questions? Go.
So what about the NF equals 0 case?
Good. So that's the case I did last time, which is pure super Yang Mills, right? So we derived that there's this Gaugino condensate, or derived, motivated, that there's this Gaugino condensate. And so that we believe the IR physics there to be NC supersymmetric vacua parameterized by the different phases I can give that Gaugino condensate.
Then
Right.
is there a superpotential?
There is no super potential there, no. Oh, sorry, I'm sorry, I'm lying. I'm totally wrong. That's a lie. Of course, this actually works, and you can think of, if I set NF equals 0, this goes as lambda cubed, and actually you can use that to derive the Gaugino condensate. So what I just said was completely wrong, sorry. So there is a superpotential, but that superpotential just goes like, there's no meson, there's just lambda cubed. And then what you can do is you can treat, so if you write your superpotential, your just kinetic term for the superpotential, tau times this Gaugino condensate, you can motivate that this lambda cubed actually generates the Gaugino condensate there. So you can still think of this as the superpotential.
Any more questions? Okay, let's thank Brian again. For those of you that are giving talks in the Gong Show, either today or